Okay, here you should be able to see all of the final answers for the derivatives that we calculated from the other day in class. And so you can check your work and make sure you haven't made any mistakes. And there's what they look like. And you might also be able to, well, let's start with a few obvious ones. It shouldn't be a surprise that the equation y equals 3x plus 5 has a derivative dy by dx equal to just 3. I mean, this is just a line with a slope of 3, so the rate of change is constant and it's always equal to 3. Another interesting one, of course, is the circle. Area of a circle is pi r squared. And when you take the derivative, you get 2 pi r, which is the circumference of a circle. If you imagine the area of a circle changing as the radius gets bigger, it's not surprising that the instantaneous rate of change happens to be the circumference of that circle, because that's kind of where you can imagine the extra area of the circle coming from where the circumference of the circle is, because the derivative or the instantaneous rate of change of a circle is going to be the rate of change of the area with respect to the radius. Okay, so I don't know if you can see the patterns here, but I'll try to point them out. Notice when we take y equals x squared, we get 2 times x, or 2 times x to the power of 1. When we take the derivative of 3x squared minus 2x, we get 2 times 3, which is 6, 6x to the power of 1 minus 2, or you can imagine 2 to the power of 0, which just gives you 2. If you don't see it yet, look at this one right here. F of x is x to the power of 4. If you bring the exponent down out front and drop the exponent by 1, you get 4x cubed, and that's the derivative. And that's actually the pattern that's called the power rule. It happens here too. Bring the 3 down, you get 3x squared. Bring the 2 down and multiply it, and you get 4x. And then the derivative of 1 is equal to 0. In fact, the derivative of any constant value is always going to be 0. And that pattern actually holds right here for the negative exponents too. If you bring the negative 1 down and then drop the exponent by 1, you get negative x to the power of negative 2, which is the same as negative 1 over x squared. And same with this one here. Bring the negative 2 down, negative 2x, drop the exponent by 1, and you get negative 3, or negative 2 divided by x cubed. So I'll take a look at today's handout right here, and it is on what's called the power rule. And here we see the power rule written in dy by dx notation. If y is equal to x to the power of n, then the derivative will always be n times x to the power of n minus 1. So with an example here, although this one's in prime notation or function notation, if f of x equals x cubed, f prime of x will just be 3 times x squared. You see the graph of y equals x cubed here. That also means f prime of 1 would just be 3 times 1 squared, which is equal to 3. And so the slope of the tangent line at x equals 1 will be equal to 3. So that's the same as the slope of this line right here, which I'll try to draw the best I can. There we go. In prime notation, we can rewrite the power rule as well. We could say if f of x is equal to x to the power of n, then f prime of x is equal to n times x to the power of n minus 1. Okay. We can also rewrite this notation. We could just say something like the following. If you have x to the power of n, then the derivative of x to the power of n, oh, sorry, let me try that again. The derivative of x to the power of n with respect to x is just equal to n times x to the power of n minus 1. So my writing's a little. So there it is, all just in one line as well. Now, as it turns out, n can be any number. It can be any integer. It could also be a fraction. It works for any value. So there are some other simple rules for differentiation. The constant rule, the constant multiple rule, and the sum rule. If k is a constant, like a number, like say 3 or 4 or 5, then its derivative is equal to 0. And that should make a lot of sense. Imagine you had y equals 5. This rule says the dy by dx is equal to 0. And that should make sense if you consider the graph of y equals 5. That's a horizontal line. So its rate of change is always 0. The constant multiple rule says if you put if you have a constant in front of a function, then the derivative is just the constant times the derivative of that function. So an example of that would be if f of x is equal to, let's say, 6x to the power of 5, then you can use the power rule, take the derivative of x to the power of 5 using the power rule, and then just multiply by 6, and that's your derivative. It's not very surprising. This derivative would be 30x to the power of 4. The next rule is the sum rule. Basically, if you're adding two functions together, the derivative is whatever you get just by adding those together. So I'll give you an example of that. Actually, here's an example right here. These rules allow us to find the derivative of any polynomial function. So 3x to the power of 4, subtract 2x squared plus 9. Using the power rule and these three rules, we know that if I take the derivative of each term, then the final derivative I get just by adding the derivatives together. So this one will be 12x to the power of 3. Okay, I'm just getting that from 4 times 3 is 12, and then dropping the exponent by 1. Subtract 4x, and then the derivative of 9, that's a constant. That's just equal to 0. Notice you could also treat 9 as 9 times x to the power of 0, since x to the power of 0 is 1. And then you could just use the power rule. 0 times 9 is 0, and so the whole thing is gone. So there's the final derivative right there. Some of these rules could be written a little differently too. This rule, I could say the derivative of u plus v with respect to x is just the derivative of u with respect to x plus the derivative of v with respect to x, using Leibniz notation there. That's how you'd write that. So in this case, u and v are not constants, okay? They're equations or whatever else. And there you go right there. In this next example, you can also use the power rule for negative exponents. I'm just going to rewrite this as y equals x to the power of negative 2, subtract 2 times x to the power of negative 3. And then I can figure out, we want to know the slope of the tangent at x equals 2. That's dy by dx when x equals 2. So dy by dx is negative 2 x to the power of negative 3. And then plus 6 x to the power of negative 4. I can also rewrite that as so negative 2 over x cubed, getting rid of the negative exponents here, plus 6 over x to the power of 4. Now we want to know the derivative when x is equal to 2, so we're going to sub in 2. There is a notation to do that that's sometimes used. It looks like this, a little bar, and then you just say x equals 2. So this is basically saying, oh, okay, now I'm calculating dy by dx when x equals 2. And I get negative 2 over 2 cubed plus 6 over 2 to the power of 4. And then it's just a matter of figuring out what that is. Let's see, that's negative 2 over 8, which would be negative a quarter, plus 6 over 16. Let's see, that's negative 4 sixteenths plus 2 sixteenths is negative 2 sixteenths or negative 1/8. Looking at the next page, some other questions here. Find the points on the curve y equals 2x cubed minus 6x squared minus 4x plus 1 where the tangent line is a slope of 3. So we're going to start by finding the derivative. And now we're using what's called we're using the power rule, which I call a derivative shortcut. So it's not necessary to do this using first principles unless we were told to. So 6x squared, take away 12x, minus 45, and then the derivative of 1 is just equal to 0. And now we're looking for when is that slope equal to 3? So, or the rate of change equal to 3. So we set 3 for dy by dx. And now we have a quadratic equation to solve. So I'll set it to 0. 6x squared minus 12x minus 45 is minus 48 equals 0. I notice that everything in this equation is divisible by 6, so I'll do that next, and I get x squared minus 2x, take away 8 equals 0, and that factors to x minus 4 and x plus 2. And so we get two solutions here, x equals 4 or x equals negative 2. Those are the two locations where this cubic function would have an instantaneous rate of change of 3 or a slope of 3. A very similar question below, a different cubic function, but in this case, looking for when the tangent line is a slope of 0 or when the derivative is 0. So again, I start with dy by dx. Okay, I'm going to get 3x squared plus 24x plus 45. Okay, and the derivative 4 is 0. So I'm interested in when that's 0, so I set it 0. And I'm going to solve this quadratic equation. Every time, I mean, the power rule tells us that if we have a cubic function, its derivative is always going to be a quadratic. Again, divisible by 3 in this case, so I'll divide everything by 3, and I get a nice simple trinomial, which factors to x plus 5 and x plus 3. And so again, I get two solutions, x equals -5 and x equals -3. So these are these 2 points on the curve, and we could find the y values if we want to, but just by back substituting x equals -5 into the original equation and substituting x equals -3 into the original equation. I'm not going to bother doing that here. And that would give you the actual points, the y values as well on the curve, where the tangent line is a slope of 0. Now that's those are interesting locations, because anytime we have a turning point on a graph, we are going to have a tangent line or an instantaneous rate of change of 0. So those are possible turning points. And as it turns out, if you were to graph this particular function, you'd find that you do have the 2 turning points. So if you think back to the beginning of the year when we started sketching polynomial functions using x-intercepts and using end behavior, we were never able to determine where turning points are. Calculus gives us a way of finding turning points on a graph now. So let's consider this quadratic equation right here. I know that a quadratic equation has a vertex or a turning point. I know that this parabola opens up. So I know that there must be exactly and only one place where the instantaneous rate of change or the derivative is equal to 0, and that must be the vertex. This gives us a nice way to find the vertex of a parabola. If I take the derivative, I'll just do it down here, dy by dx is equal to 4x take away 8, and then I set that to 0. Okay, 0 equals 4x minus 8, which means that 4x equals 8, x equals 2. So x equals 2 is the location where the rate of change is equal to 0, and that must be where the vertex is. I can find the y value of the vertex just by substituting. X equals 2. And let's see, what do I get here? Well, that's 4 times 2 is 8. 8 minus 16, take away 1, which I believe is -9. And so we have a vertex at 2, -9. A really nice way of finding a vertex without completing the square or doing anything else like that. So there it is. There's the power rule. Hopefully that helps. There's some questions from your textbook that you can do. If you don't have your textbook at home today, perhaps you could get a friend to take a picture of that for you and send it to you. I don't actually have a textbook with me, and I'm not in Port Elgin today, so unfortunately I can't scan those for you. Do your best to try these questions, and we'll take a look at them tomorrow. Okay, thanks.